So, good afternoon, everyone. My name is Gabriel Magni. I'm Adequacy and Market Modeling Specialist at the European Network of Transmission System Operators for Electricity, so ENTSO-E. My work mainly focuses on the Pan-European Resource Adequacy Assessment, so the ERAA. And today I will be presenting one of the central steps within this ERAA process, which is the Economic Viability Assessment, and more precisely, I'll be focusing on one of the implementation approaches, which is called the revenue-based approach. I will start the presentation with a more general overview of the ERAA as a process, before then focusing more on the revenue-based EVA itself. So, ENTSO-E is legally mandated to prepare the ERAA on an annual basis. So it's an adequacy analysis that takes the form of a report that is published and submitted for approval to the Agency for the Cooperation of Energy Regulators in the EU, so ACER. The aim of the ERAA is to assess the adequacy risks of the European power system in the medium term, so in the next 10 years, while focusing on specific pivotal target years, which are then explicitly modeled and simulated. The key role of the ERAA is to inform decision makers and the stakeholders about these identified adequacy concerns and risks for them to be able to then make more informed decisions. And the ERAA also acts as a reference for member states to introduce capacity mechanisms in their countries. Additionally, the ERAA also strengthens Europe's energy transition by complementing other planning studies and through its transparent data. Now, regarding the scope of the ERAA, it's a pan-European study. So on the map on the left, you see the regions that are covered by this assessment. In blue, we have the regions that are explicitly modeled and simulated, while in green, we have, for instance, Morocco and Tunisia, which are not explicitly modeled, but their impact on the explicitly modeled regions are taken into account. Then, regarding the network modeling in the ERAA, we use zonal flow-based market coupling for both the core region, which is highlighted on the center map, and then also for the Nordic region, highlighted on the map on the right. Next, about the general process of the ERAA itself. So the starting point, so from the left, is of course the input data collection. So we collect most of the data from our members, from the TSOs, for instance, regarding net generation capacities, also market coupling related data, such as net transfer capacities and flow-based domain related parameters. We also utilize the Pan-European Climate Database to calculate the capacity factor profiles for renewable technologies, also hydro-related data, such as hydro inflows, and temperature profiles, which are then used to produce the demand time series for our different market nodes. All of this data then makes up what we call the national trends scenario, which is based on the member states' national energy and climate plans. However, this data is not used as is directly to perform the adequacy analysis itself, but first we subject it to which will be the main focus of today, so this Economic Viability Assessment. And what it does is essentially we assess, as the name suggests, which capacity is economically viable. Capacity that is deemed unviable will be removed or decommissioned, and while considering, of course, new capacity additions in case those would be deemed viable. So it is only after we perform this change or this modification, let's say, to this original scenario data that we obtain the central reference scenario for the ERAA. And it is this data and scenario that we then use to perform the main adequacy analysis itself, which is performed as a Monte Carlo simulation, where we have 36 independent climate years, or what we call also referred to as also weather scenarios, and 15 independent unplanned forced outage draws. In total, we get then 540 Monte Carlo sample years, which we then use to compute the main adequacy metrics, which are the expected energy not served and the loss of load expectation. So next about the EVA. So as I mentioned, the EVA objective is to assess the market-based investment signals and determine whether capacity is economically viable under the given scenario and assumptions. Now, according to the electricity regulation and methodology for the ERA, there are two different implementation approaches that are possible. We have what is called the cost-based approach, where the objective is to minimize the overall system cost, including investment cost. This is your more traditional generation expansion planning type of problem. And then we have what is called the revenue-based approach. So here, the assessment of the viability is done based on the differences between the revenues and the cost of the units. And of course, we shall keep existing viable resources in the market while considering new viable capacity additions when possible or when they are deemed viable. So this revenue-based approach will become clearer when we go through some of the following slides focusing on that. For your information, so up until now, so up until ERA 25, for instance, we have been implementing the cost-based approach in order to produce the central reference scenario. But already since ERA 24, in parallel, we've also implemented as a proof of concept this revenue-based implementation approach, and with the aim that we would transition for future ERA editions to this revenue-based approach, possibly already for ERA 26. Motivation behind that will be also become clearer in the following slides. Now, before going to the revenue-based approach itself, a very general overview of the cost-based implementation. So, as a problem type that we are trying to solve, it's a stochastic multi-year generation expansion planning problem, where, as I mentioned, we minimize the investment cost and the operational cost across the different weather scenarios and years. The result or the output is a cost-optimal system with the least cost generation mix and dispatch. And in ERA, we use a linear formulation of this problem in order to keep the problem tractable. And the implementation itself is, of course, done. We utilize Plexus's long-term plan feature, which is especially suited for generation expansion planning type of formulations. Now, the cost-based approach has certain limitations when it comes to within the context of the ERA. So for a pan-European scale stochastic study, this approach can easily become computationally intractable. And thus there are computational or modeling simplification, rather, that are needed. This include, for instance, aggregation of thermal units into technology bands. So there we have a loss of unit-level granularity. Perhaps most importantly, most notable limitation is that we are only able to include a very limited number of weather scenarios in this stochastic optimization. So for ERA 25, we were able to include 3 weather scenarios out of the total set of 36 weather scenarios that were included in the ERA assessment itself. Of course, behind this, there's a weather scenario selection process. So we aim to select the 3 most representative ones of this whole set with regards to revenue distributions. However, of course, 3 weather scenarios will not be able to capture all the details or dynamics of the full set of 36. In addition, we have certain technical constraints that are omitted or modeled in a more simplified way. Then, regarding the modeling of different risk, investor risk aversion behavior, it is also, let's say, more limited in the cost-based approach, at least without more significantly impacting the computational complexity of the problem. And regarding the interpretability of the results, it can sometimes also be rather more difficult to really understand how or why a specific EVA decision was made by the solver, because you only have access, let's say, to the optimal results. So, these limitations, let's say, are the motivation behind this transition towards this revenue-based framework, which I will then go into more detail in the following slides. So the revenue-based methodology or approach, so it's an iterative market-driven approach, which in theory, under a specific set of assumptions and conditions, there exists an equivalence to the cost-based approach in that they converge to the same solution. However, now in the context, when applying this to a stochastic multi-year analysis, this equivalence does not necessarily hold, and we do observe different, let's say, results between the two approaches. Now, this bottom diagram shows the core concept of this iterative approach, so I will walk you through it. So the starting point is the initial system. We have the initial resource capacities. We perform for this initial system a first economic dispatch market simulation. From this, we extract the revenues of the units, and we perform this economic viability check by comparing the revenues with the costs. We do this by essentially with this metric called EBITDA to evaluate essentially just the profitability of the units, let's say. Then we ask ourselves whether there are any units that are missing money in the system, and or if there's sufficient revenues in the system that would incentivize additional profitable investments. If the answer is yes to either of those, then we update the capacity mix, we remove the least viable assets, and add the most profitable investments to the system. So we make this update to the capacity mix, and then we perform again another market simulation. So then we keep doing this iterative approach until we reach a converged system state, which is what we can call at equilibrium, which means that all units in that system are economically viable, and there is no additional profitable investments that are possible. So that's the core concept of this approach. Now, next, I will go a bit more in detail on how it is implemented in practice. So during ERAA 25, there were two different implementation approaches for the proof of concept. So I will walk you through both. Starting with approach A. So on the bottom left, we have this very simple graph with the initial system state. So we have 4 different technologies with initial capacities. What we do before we launch this first economic dispatch simulation is we saturate the system with what we call dummy units, which corresponds to the expansion potential. So this should be selected sufficiently large as to not restrict, let's say, the ideal expansion that could occur by this EVA approach. Then here the existing units and the expansion candidates are essentially competing against each other in terms of profitability. And then at each iteration, we only take decommissioning decisions. So for instance, we perform our first iteration, we decommission part of the existing capacity, part of the expansion potential. We reach this system state, we perform another iteration, and let's say now we've reached convergence. And what is left now of the expansion potential of these dummy units, this corresponds to what has been expanded or commissioned by this revenue-based approach. Approach B uses slightly different logic. Here, instead, we include initially very small dummy units of the different expansion candidates. So these would be just of 1 megawatt, for instance, in size. So they are not really influencing the results of the first iteration. But what it does allow us to do is to evaluate the profitability of these technologies on a per megawatt of capacity basis. So then at each iteration, we are able to perform both commissioning and decommissioning decisions based on the profitability. So here, just as an example, both decisions are being made simultaneously until we reached a converged system. Now, up until now, I've been focused on the core iterative loop, let's say, a main principle. But of course, the ERAA is a stochastic multi-year analysis. So next, I will explain a bit more in detail how this is applied in that context. So again, there are 2 different implementation approaches, A and B. But I will start with the approach A. So here, maybe just to clarify, TY corresponds to target year, and IT corresponds to iteration. So iteration being one set of ED simulations, as explained in the previous slides. What we do in this approach, so we start by assessing the EVA decisions of the first target year. So we perform this iterative approach for the first target year, as was previously explained. Here, within each iteration, the decisions are based on the expected revenues across all the weather scenarios, meaning that, so this is the way how we take into account the uncertainty, let's say, across the different weather scenarios. And within each iteration, we are essentially running n number of parallel simulations, so corresponding to the number of weather scenarios that we are taking into account. So we are performing this until convergence. However, in parallel, we are also running the following target years. So the same exact process run independently or in parallel of one another for the following target years. And the reason for this is because at the end of the day, we need to assess the profitability over the lifetime of the units. So this is why we then compute this also for the future target years in order to be able to take into account the expected revenues from these future target years. So once all target years have converged, then we make essentially the decisions for the first target year, considering the lifetime of the units. And we do this by calculating the net present value, taking into account the expected revenues from these future target years. Here, unit is expanded for the first target year, only if it is, well, firstly profitable in the target year and has a positive net present value, and a unit is decommissioned if it is unprofitable in the first target year and has a negative net present value. Then these decisions are fixed for the first target year. So we are done with the assessment of the first target year, and we pass on these decisions when we perform the assessment for the next target year. So we perform the same exact process now for target year 2, while simulating also the following target years, so target year 3 as well. Perform this iteratively until we perform ultimately the assessment for the last target year and it reaches convergence. So this is the approach for implementation A. Now, implementation B has some differences for approach A, but the core concept when it comes to assessing one target year at a time still holds, as can be seen from this staircase structure of this diagram. I'll highlight the main differences here. So here, within each iteration, we are not taking, we are actually taking into account the expected revenues from the future target years. So we are assessing target year 1, but we are now also between each iteration, we are taking the net present value essentially into consideration when making these decisions. And here it's important to highlight we are only making decisions for target year 1. So this is essentially an assumption that we are taking for this approach, where essentially the investor has a limited foresight on the future, limited foresight, so it is not expecting investment decisions to be taken in the future target years when it is itself considering decisions for the target year that is being assessed. So it's, let's say, a myopic investor behavior or view. So that's the main difference, and otherwise, similar approach until we reach convergence of the last target year. Now, regarding the advantages of the revenue-based approach, so firstly, having the ability to intervene how each investment decision is made provides a lot of flexibility regarding the risk aversion modeling, and to give some examples here. So, for instance, we are able to derate or exclude a certain share of revenues coming from peak price periods, for instance, because investors perceive revenues or the risk associated on relying on revenues coming from scarcity periods differently from, for instance, revenues coming from normal operating hours. And here this is easily possible in this iterative approach to take into account. Similarly, we can vary the level of risk perceived by the investor based on the annual operating hours, which is also an element which impacts, let's say, the risk perceived by the investor. Then regarding computational performance, so when applied in this ERA context for a stochastic pan-European study, it's solving many smaller problems. So essentially, we're solving many small economic dispatch simulations instead of one large generation expenditure planning problem. Can improve the overall performance of the simulations, but and notably, it improves the scalability of the problem. So here, we are able to include many more weather scenarios in this assessment of the EVA, because ultimately, the complexity of each simulation doesn't increase here. Instead, we are simply running more simulations in parallel. So, And then regarding interpretability of the results, here the iterative approach also allows to trace back how each of these investment decisions were made between each iteration, and this really gives more insights into the results and allows us to better understand why a specific decision occurred, for instance. Then regarding the implementation pipeline, which is enabled by Plexus, and especially we utilize Plexus Connect for coordinating and launching the simulations, and the Plexus API to really implement this in an automated and efficient way. So in this diagram, we have two main independent modules. We have the model builder module on the left, which, as the name suggests, is responsible for building the model. So it takes the input data, outputs the model data files that we upload on Plexus Connect. It outputs the starting model, the model XML, that is fed into the revenue-based script, which then performs this first modification by adding these dummy units to the model. Automatically, it is then uploaded to Plexus Connect, where the simulations are launched. Once the simulations terminate, we have the results. They are then extracted, and we perform the processing. So we perform this economic viability check. Ultimately, we are asking whether the model has converged. If not, we keep doing another iteration. If yes, then we have the final results. So to conclude, the ERAA methodology supports two different implementation approaches for the EVA. While we have been using the cost-based approach historically, due to practical limitations, this motivates the transition towards this revenue-based framework. And by leveraging market simulations in Plexus, and the Plexus Connect, Plexus API, we are able to effectively and in an automated way implement this revenue-based approach. So I hope you learned something from this presentation. And thank you for your attention, and open for any questions.
I have a gap in my understanding. I think you say the revenue-based approach. Could you go back to the conclusion slide? You model risk aversion by doing that approach. Can you explain how that happens? I don't understand how that relates to each other.
Yeah. Okay. Yeah. Well, there are different ways to model risk aversion, but with this, for instance, what I mentioned in the example about modeling risk aversion of the investors with regards to, for instance, revenues coming from scarcity periods, because investors can perceive the risk associated in relying on revenues coming from scarcity periods differently instead of relying on revenues that come from normal operating hours, for instance. So here in the revenue-based approach, at each iteration, when we extract, for instance, the revenues, we are able to, at that point, decide, okay, we derate these hours where they come from peak price periods by this much, for example, or we exclude a certain amount. So there's a lot of flexibility on how to model this.
Sorry. Thank you for the presentation, and always good to see the progress that has been done over the years. Two questions which are kind of related. Will you share some backcasting results to support the fact that the revenue-based approach will be able to replicate actual electricity prices, especially for the first few years? And B, to what extent do you include the revenues generated from the other markets, say ancillary services or imbalance market as well, in the revenue-based assessment, especially for flexibilities?
Yeah, thanks. Those are good questions. So on the first point regarding the shift towards this revenue-based and how do we measure, for instance, whether it is accurately capturing or whether it's an improvement from the cost-based. So for this, well, I would need to check internally whether we will also be publishing this. However, yeah, we do conduct, for instance, consistency analysis. We, for instance, compare how does the revenue distribution look in the EVA, and then after, once we perform the economic dispatch, it's the adequacy analysis itself. So we compare how consistent the results are between those two, which is a very important metric, which is also one of the motivations to transition overall, because having only 3 weighted scenarios implemented in the cost base results in the consistency not being that great, for instance, compared to the revenue base where we are able to increase this substantially. And then regarding the second question, could you just remind me perhaps of the second question? Sorry.
Or the revenues.
Yeah, sorry. Yeah, on the other revenues. So for this one, so at the moment, the main focus was really on the energy, the revenues coming from the energy-only market. But we do already model or include in our models the balancing capacity reserve market. So there's the co-optimization of the balancing capacity with the energy. And that does allow us to take into account revenues coming from the balancing market. What we do not model, for instance, at the moment is the activation of these balancing capacities. So the activation market is not taken into account at the moment. But yeah, I will have to say, so these different revenues, so the aim is, of course, to capture all relevant revenues for the different resources. And this is something that we are working on and developing further to try to really make sure we capture all the relevant revenues that would impact these economic commission or decommission decisions.
We've got time for one very quick question.
Okay, very quick. Thanks for the presentation. Like there you, in the revenue-based approach, you presented 2 different methods. And could you explain quickly a bit more on the differences and the pros and cons? And which one did you use in the report?
Mm-hmm. So at the moment, so given that these are proof of concept, maybe I'll go to this slide. Let me just put them side by side. So given that these are proof of concepts, we included these during the ERAA 25 publication in an annex, where you can find also some information on these. So there is no yet, let's say, clear decision whether we would favor one over the other. But there are different underlying assumptions essentially to these 2 approaches. So the approach A is approach where the investor, let's say, is more future aware. So it's making the decisions for the first target year, anticipating that the system in the future target years is at an equilibrium state. Whereas in the approach B, we have an investor who is, does not have this anticipation. So instead, it is more, has this myopic view. And it is possible, for instance, that it's making decisions in the first target year. And once we simulate we perform the assessment until the end, it could be that investments that were made during the first target year are no longer necessarily profitable. So that's possible, and that comes down to the underlying assumptions behind the risk aversion modeling or the investor behavior that we want to capture.
Lovely. Thank you very much.
Thank you.